Hello everyone. In finite element analysis, we can mesh any complex assembly and include a fine level of detail. However, this is not always the most efficient approach, especially for portions of our model that are not of primary interest. For example, we may have many fasteners connecting two parts together. Now suppose we want to determine how the loads are transmitted through the fasteners, but we aren't interested in the stresses at the fastener locations. Is there a more efficient way to represent this? In cases where we want to reduce the local behavior of many nodes to just 6 or fewer degrees of freedom, a remote point may be the answer we are looking for. In this video, we will learn how remote points work behind the scenes, how to define them, and discuss certain aspects of remote points to be aware of when using them. Let's get started. Let us first see what are remote points and where they are used. Remote points are used to approximate the behavior and kinematics of certain portions of the geometry with a single point that has 6 degrees of freedom. It can be scoped to any geometry with the remote point defined at any arbitrary location. Remote points can be used to apply remote boundary conditions and perform many other simplifications. For example, replacing a rigid body that is not of interest with a remote displacement boundary condition, simplifying the modeling of an actual revolute joint, approximating a body as a point mass. All these simplifications aid in reducing the solving time as well. But how is a remote point associated with the scope geometry? A remote point is represented by a node in space called a pilot node. This pilot node or remote point is connected to the geometry via the use of multi-point constraint or MPC equations. MPC equations define the relationship between the degrees of freedom of the scope geometry and the 6 degrees of freedom of the pilot node. Thus, MPC equations tie the nodes of the scope geometry to the pilot node. The scope nodes are generally solid nodes with 3 degrees of freedom, while the remote point is a single point representing the kinematics of the collection of scope nodes. Hence, a remote point always has 6 degrees of freedom, 3 translations and 3 rotations. An added advantage of this fact is that we can scope a remote point to a solid body that only has translational degrees of freedom and use it to apply a rotation to the solid body, which would not have been possible otherwise. These additional MPC equations are added to the structural matrix equations or equations of motion. So how do the MPC equations work? Let us have a look. Let's say we have 3 unknowns A, B and C that we need to solve for in the given set of equations. Now say there is an additional constraint of A equal to B plus C that must be satisfied. Because this is an extra constraint, we can't impose this after solving for A, B and C separately with our original set of equations. We need to make A a dependent variable and substitute A with B plus C in the original equations. We can then solve for B and C first since they are independent variables, and then calculate A using the constraint equation A equal to B plus C. MPCs have independent and dependent degrees of freedom. Dependent degrees of freedom are removed from the matrix equation by processing them in stiffness matrix first. The dependent degrees of freedom are removed from the set of equations while the independent degrees of freedom are retained. We solve for the independent degrees of freedom and then calculate the values of the dependent degrees of freedom by processing the MPCs. The solver automatically assigns the dependent and independent degrees of freedom based on the behavior of the remote point. A remote point can have rigid, deformable, coupled, or beam behavior. Let us first discuss the rigid and deformable behaviors which are frequently used. Rigid behavior is generally used when the entity whose kinematics are being approximated by the remote point is very stiff compared to the part of interest. When the rigid behavior is used, all the nodes in the scope geometry will have zero relative displacement to each other. But the scope geometry can deform with respect to the rest of the geometry. On the other hand, deformable behavior is used when the entity being represented by the remote point has much less stiffness as compared to the model geometry. This can be seen in the following example. Suppose we have a plate with a hole. The plate is fixed at one end and is subjected to pressure on the other end. If the nodes on the inner surface of the hole are tied to a remote point with rigid behavior, the deformation is constant for the entire face of the hole. That is, relative displacement of all the scoped nodes is zero, and the hole remains circular in shape even though the hole itself may translate in space due to the loading. However, if the behavior of the remote point is set to deformable, then the inner face of the hole can deform and the hole no longer retains its circular shape. Let's look at some additional considerations to keep in mind when choosing the behavior of a remote point. For rigid behavior, the pilot node or the remote point is the master or independent degree of freedom. The degree of freedom of the nodes of the scope geometry are the dependent degrees of freedom that are eliminated by the solver prior to solving the system of equations. This means we end up with 6 times n sets of constraint equations or MPCs for every remote point. On the other hand, for deformable behavior, the pilot node or the remote point is the dependent degree of freedom, and the degrees of freedom of the nodes of the scope geometry are independent degrees of freedom. This means we have only 6 constraint equations or MPCs for every remote point. With the rigid behavior, you end up with a lot of simple internal constraint equations that are easy to process. With the deformable behavior, you end up with 6 internal constraint equations that are complicated. So to eliminate the dependent degrees of freedom, we may need a lot of computer memory. That is why it is recommended to not scope a deformable remote point to too many nodes, since it may take up a lot of CPU time and memory to process. Also, with rigid behavior, the pilot node is the independent degree of freedom. So you can apply a force, moment, displacement, or rotation boundary condition directly. With deformable behavior, ideally you should only apply force or moment boundary conditions. Displacement or rotation boundary conditions should not be applied to a remote point with deformable behavior, since the degrees of freedom of the remote point are the dependent degrees of freedom that will be eliminated by the solver. If displacement or rotational boundary conditions are applied to a deformable remote point, the solver will reorder the equations before solving, but it is generally recommended to avoid such situations. Let us now investigate other behaviors, coupled and beam behavior. The coupled behavior gives users the flexibility to specify that nodes scoped to the remote point all move together with the same value in x, y, and or z directions. In practical situations, this option is not often used, but is available if such a unique constraint condition needs to be imposed. The beam behavior is useful when using the spot weld feature to connect surface bodies together, but that is outside the scope of this lesson. Before proceeding to the demo, we should make note of a few important points. Firstly, Note that we are simplifying the behavior of an entire part by representing its kinematics by a single remote point. Thus, we are making assumptions about the behavior of that part and not considering its actual stiffness. Hence, if that part is in the region of interest, it should be modeled with actual geometry and contact should be used instead of representing the interactions via a remote point. Secondly, the region of two remote points should not overlap. Always promote a remote boundary condition to a remote point and reference the common remote point if needed in another object. Thirdly, deformable behavior should not be used on surfaces that are modeled with symmetric boundary conditions. And lastly, thermal stress analyses pose some problems because a remote point may prevent thermal expansion or contraction and thus cause an overconstraint. For example, either the rigid or the beam behavior of the remote point will prevent thermal expansion and high stresses may develop. We will now proceed to the demo and see how use of remote points simplifies our model. Here we have modeled a mechanism which consists of two levers A and B connected to each other by a pin. A block C is connected to the lever B. This mechanism is a part of larger assembly. It is in a lock position where lever A can only rotate about an axis but cannot translate in any direction. Lever B can rotate about lever A and is pulled by force acting on block C. The force acting on block C is due to another part of the mechanism which we have not modeled here. We are interested in seeing the deformation and stress generated in this portion of the mechanism when a force is applied on the block C in the Z direction. All the components are composed of structural steel. Bonded contact has been defined between lever B and part C. We also have contacts defined between the pin and the two levers. A revolute joint has been defined between the ground and lever A. All the parts are meshed with elements of size 3 mm. We will now utilize remote points to simplify certain portions of this assembly. Note that levers A and B along with the pin form a revolute joint. Instead of modeling the geometry of the pin and the contact between the pin and the two levers, we can define a revolute joint between levers A and B. To do this, let's suppress the pin. In the tree outline, right-click on the pin and choose Suppress Body. This also suppresses the contacts between the pin and the two levers. Next, right-click on Joints, Insert Joint. Under Details of the joint, set the connection type to body to body. Set the joint type to be revolute. Make sure the Face Select option is active. Select the inner surface of the hole on lever B to be the reference side and click Apply. Similarly, select the inner surface of the hole on lever A to be the mobile side and click Apply. We can see that a revolute joint is created such that the mobile lever A can only rotate with respect to the reference lever B about the local Z-axis. All other degrees of freedom of mobile lever A are restricted with respect to the reference lever B. ANSYS Mechanical implements such joints by creating remote points internally. In this case, by default, the remote point has rigid behavior. Next, let's apply a force in the global Z direction on the part C. We will use remote force to apply the force acting on block C because the component applying force on block C is not modeled here. So right-click on Static Structural, Insert, Remote Force. Make sure the face select option is active. Choose the face of part C as shown and click apply. Under details, set the define by to components and set the Z component to 1000 newtons. We are assuming that the part in contact with block C for which we are applying the remote force is rigid, and hence we will set the behavior of the remote force to be rigid. Note that when remote boundary conditions are used, ANSYS Mechanical creates a remote point internally. In our case, it will create a remote point whose behavior is rigid. Another important thing to note here is that by default, ANSYS Mechanical creates a remote point at the centroid of the scope geometry, but this location can be changed manually to modify the location at which this force is applied. For example, if we rescope the remote force to the side surface of block C, we see that the location of force application remains unchanged. Thus, it is important to visually confirm that the location of load application is correct when using remote boundary conditions. This is an important thing to keep in mind if you change the scope of a remote boundary condition or duplicate an existing remote boundary condition. Also note that in this configuration, the applied remote force would also create an additional moment due to the offset between the point of application of the force and the centroid of the scoped surface. Thus, remote force allows us to mimic a rigid body attached to our geometry by applying a force at the relevant location. Let's revert back to scoping the remote force to the top face of part C. Next, we need to constrain the displacements and rotations of this surface in all directions except Z. Creating a new remote boundary condition and scoping it to the same surface would lead to the model becoming over-constrained. To avoid this, we follow the correct method, which is to promote the remote force to a remote point and then use that remote point to define a remote displacement boundary condition. So right-click on remote force and click on promote to remote point. A new remote point is created under the tree outline. Also notice that in the details of the remote force, the scoping method has changed from geometry to remote point, and the location and behavior of the remote point have now been grayed out. Now these changes can only be made to the promoted remote point under the tree outline. Finally, let's use this newly promoted remote point to constrain the rotations of the block C and its displacements in the X and Y directions. Right-click on Static Structural, Insert Remote Displacement. Change the scoping method to remote point and select the remote point that we promoted just now. Define the displacements in X and Y directions and all the rotations to be 0. Before we solve this problem, let's take a quick look at the analysis settings. We leave large deflection to be off since the mechanism is locked, and under its current configuration, we do not expect large deformation to occur. Now we are all set to solve this model. Right-click on Solution and choose Solve. Let's take a look at the various results. Right-click on Solution, Insert Deformation Total. Again, right-click on Solution, Insert Stress Equivalent. Right-click on Solution and choose Evaluate All Results. We can also track how the remote point is deforming under the applied loads by using the deformation probe. To do this, right-click on Solution, Insert, Probe, Deformation. Under the details, set the location method to remote points and choose the relevant remote point. Now right-click and choose Evaluate All Results. We can also obtain the reaction forces at the two joints by simply dragging and dropping the two revolute joints to the solution branch. This creates two joint probes that give us the reaction forces on the mobile portion of the joints. In this case, the mobile portion of both the joints is lever A, and we can see that the two forces balance each other out. Finally, we can obtain the reaction force due to the remote displacement on block C by dragging the remote displacement boundary condition and dropping it on the solution branch. This creates a force reaction object which gives us the reaction force generated on the mechanism due to the applied loads. If we draw a free body diagram of lever B and block C, we see that a force acts on the whole of lever that is equal and opposite to the force we obtained through a joint probe of the revolute joint between levers A and B. A force of 1000 Newton acts in the global Z direction on block C. By balancing forces in all directions, we expect a reaction force of 1000 Newton to act in the negative x direction, which matches the value in the force reaction object. Thus, we have demonstrated how to reduce the total number of degrees of freedom in a problem by utilizing remote points. Now let's summarize the key takeaways. Firstly, remote points can be utilized to simplify the kinematics of certain portions of the geometry. In ANSYS Mechanical, remote points are utilized in many objects such as joints, springs, beam connections, point masses, moment loads, remote boundary conditions, among others. Secondly, multi-point constraint or MPC equations are used to tie the behavior of a certain portion of the geometry to a single point. Since the single remote point represents the kinematics of a collection of nodes, remote points have 6 degrees of freedom, 3 translations and 3 rotations. The remote point can have deformable or rigid behavior. Rigid behavior is generally used when the entity whose kinematics are being approximated by the remote point is very stiff compared to the part of interest. Deformable behavior is used when the entity being represented by the remote point has much less stiffness as compared to the modeled geometry. The region of two remote boundary conditions should not overlap, or that could over-constrain the problem. Instead, it is better to promote the remote point and reuse it in multiple remote boundary conditions. Finally, we need to take care when using remote boundary conditions and visually confirm the location of the remote point where the load is being applied. We hope you have found this video informative. Thank you for watching and do visit our channel to discover more useful learning resources.